Welcome back to our series on probability theory. I'm Mark Ledbetter, and this is lecture video 41, part B. We are discussing univariate transformations, or functions of one random variable. In the last video, we discussed transformations on discrete random variables, and we found that we have advice, but we don't have a theorem or a formula that we can plug into to get the answer. We have to think it through. And usually it involves drawing out some tables of the PMFs and making sure that we map the values directly. And we're also using an inverse function. So if it's 1-to-1 function, then we only have one inverse function. If it's a 2-to-1, 3-to-1, etc., then we may have multiple inverse functions. But we need those inverse functions to substitute in for x if we're going from x to y. All right. And so in this video, we are going to discuss univariate transformations on continuous random variables, and we have a theorem for this. And the first theorem we're going to discuss is a theorem for a 1-to-1 transformation, a function that is 1-to-1. So that makes the inverse very simple. There's only one of them. So as I mentioned last time, we did this example where we were dealing with a binomial distribution. So x has a binomial distribution, parameters n and p, and if we choose a 1-to-1 function, then we're going to have the same number of values in the support of y as we do in the support of x, and so we will have the same probabilities in this support of or in the PMF of y as we do in x. They just may be in a different order. So here we are going to use the binomial, and we're going to make this 1-to-1 transformation, y equals e raised to the x. And what we did was we wrote out the PMF of x, and we plugged in the parameters that we had, and we wrote the space of x, or support of x, and then we found the inverse transformation on y. So x equals a function of y, the inverse function, which was e to the x. The inverse of that is a log. And log is always base e in statistics unless it's otherwise notated. And then we simply plugged in to the PMF of x, substituting in for that function, that inverse function of y. And then we had to make sure that we found the individual values in the support of y. Okay? So for discrete distributions, there is no theorem or general formula. For y equals u of x, we're going to find the inverse of u of x. And so we're going to end up with x equals the inverse of y, function of y. And if y is a 1-to-1 function, we simply substitute x equals the u inverse of y for every value of x, and that was in example 2. If y is a 2-to-1, m-to-1 function, then we need to use a table or tables and determine the distribution of y as we did in example 1. Now we're going to switch to continuous random variables, and there is a theorem or a quote-unquote formula that you can use. But the first method that we're going to discuss is called the CDF, the Cumulative Distribution Function method. And this is when y is 1-to-1. Okay? It's a 1-to-1 function of x. So let's do this by example. This can be a very complex method, or it can be a very simple method, depending on how complex your PDF of x is. So let's start off with x being distributed as f of x, which is 4x cubed when x is between 0 and 1, and of course 0 otherwise. And then we're going to let a denote the space or support or range of x. Space, support, range of x. And we're going to let b denote the space, support, or range of y. Okay? And so we have y equals negative 8 log x. Now, how we find this support or space or range of x is we look at the range of x, or sorry, this was of y, b is for y. We look at the support of x and we make substitutions into our formula. So when x is 0, log of x would be negative infinity. If you remember that the log of x crosses at 1, and when x is less than 1, it gets negative. And as it approaches 0, x approaches 0, y approaches negative infinity. But I have a negative out here. So a negative times a negative gives me a positive, so I end up with a positive infinity. And then when I look at 1, I plug in 1 for log of x. Log of 1 is 0, so y is 0. So I'm mapping that. Now you have to be careful. If it's not a continuous, if it's a function that's broken or has a gap or holes, or it's not defined as continuous on the whole range of x, then you have to be very careful. Or if it's a piecewise, you have to look at the different steps or different segments of x and make sure that you don't miss anything. Okay, so that is a caution for you to be careful. All right, so we want to find the PDF of y. In other words, we want to find g of y. We're going to use the CDF. We're going to define the CDF of y. So g of y, and we're going to write it as a probability that y is less than or equal to y. And now that we have y, we're going to make the substitution for y, and we just simply substitute in for y. Now what we have to do is solve this in terms of x. So we're going to have to take the inverse transformation. Please do this inside the function. This is the best way to not get lost and get your signs wrong. Because if you get these signs wrong, you don't have a PDF anymore. You have junk, okay? So we don't want junk as our result. We want a good PDF, or CDF in this case, and then we'll get a good PDF when we're done. All right. So the first thing we do is we multiply both sides of the inequality by a negative 1. And so when we do that, we have to change the sign of our inequality. What we're trying to do is isolate x by itself. So we're going to divide both sides by 8 now. 8 is positive. We don't change the sign. And then we're going to take both sides and make them the exponent in e. E is positive number, the natural number e. So the sign stays the same again. And when we take, this is where you need to know your algebra, e raised to the log x, where log is the natural log, is simply x. Okay? So we end up with x, and then we end up with e raised to the negative y over 8. So the probability that x is greater than or equal to e to the negative y over 8. Now, to get what this is equal to, we are going to integrate this, and we're going to find this probability, because this probability, in terms of x, is the CDF of y. Okay? So, what we're going to do is we're going to take the integral now. It says greater than this value, so that is the lower limit in our integral. Remember that for continuous distributions, you're always integrating. You're not using summation. You're integrating. Okay. And so we have to look at the space of x up here, and we see that x goes from 0 to 1. So the maximum value that we can have is 1. So we integrate from this value up to 1, and f of x is 4x cubed from between 0 and 1, and then dx, and please write your dx so that we know that we're integrating and that we have everything. And so when I integrate x cubed, I add 1 to the exponent, that makes it a 4, and then I divide by that exponent. So I'm dividing by 4, and so I see that the 4 divided by 4, those cancel, and I'm left with x to the 4th, and that goes from x equals e to the negative y over 8 up to 1. And so I first plug in 1, and that gives me 1 to the 4th, which is 1, and then subtract, and then I plug in the bottom limit, e to the negative y over 8. Well, e to the negative y over 8 to the 4th, what we do is we multiply exponents. That gives us e to the negative 4y over 8, which is e to the negative y over 2. Here I do encourage you, if it's in an exponent, to simplify, unless we're looking for a specific form of a PDF or CDF so that we can identify the distribution. But in this case, we're not trying to identify that distribution. We're trying to find the PDF. Once I have the CDF, then I can take the derivative with respect to y to get the PDF of y. And so taking the derivative of this gives me 0 for the first term. I have a negative e, so let me write this out quickly. So d dy e to the negative y over 2, and I'm going to put a negative out here for this negative. So I have that here. Then this is going to be, I'm taking the derivative, so I'm going to take the exponent, the derivative of e to the u is equal to d du, e to the u is just e to the u. But here I also have to do du dx, or dy in this case. Chain rule. So I have negative e to the negative y over 2, and then I have to take the derivative of u, which is going to be negative 1/2. So I end up with 1/2 e to the negative y over 2 for y between 0 and infinity. Remember, we use b here, and 0 otherwise. Okay. So in the next video, we will start with the transformation theorem. And then we will go from there. So please don't forget to scan and upload your lecture notes before midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't make it to virtual office hours before you need an answer, then by all means email me. But when you email me, I need 2 things. I need a picture of the problem because I may not have it handy. And second, I need a picture of your work so I can see how you're approaching the problem. And then I'll be able to help you quickly through email. So please take care of yourself, stay safe, and we hope to see you next time.